Lowry's theory defines acids as electron pair acceptor and bases as electron pair donor. So, and how can we identify Lewis acid and Lewis base? So, for Lewis base, let's say we have ammonia. All right. So, first thing you have to do is that you have to take out the central atom. The central atom is that atom in a compound to which the rest of the atom in the compound are attached to. Okay. And in case of ammonia, nitrogen is the central atom. Okay. So let's pick the nitrogen out. Okay. Nitrogen. Then nitrogen is atomic number 7, which means that it will have 5 valence electrons. So let's fill out the configurations. We have 1s2, 2s2, and 2p3 rather. Okay. All right. So since nitrogen have 5 valence electrons, it means it will have 5 valence electrons. It means these two orbitals, they are the valence orbitals. These two orbitals are the valence orbitals. And in that case, let's draw their configuration out. I mean they are subshells. Okay. And filled in the electrons. As you can see here, the number of unpaired electron equivalent to the number of bond we have in ammonia, while the number of paired electron, because this is a paired electron, we have 2 electrons in an orbital. We call it paired electrons or electron pair. We have single electron in an orbital. We call it unpaired electron or single electron. Okay. So, and when we have no electron in an orbital, we say the orbital is vacant. All right. So in this case, now we have 1 paired electron, and that paired electron is equivalent to what we call lone pair. This means that if you draw a Lewis structure for ammonia compound, we see that we have what? We have 1 lone pair and 3 bond pair. So the 3 bond pair equivalent to the number of unpaired electrons, while the lone pair, this one, equivalent to the number of paired electrons or electron pair. Alright, in a nutshell, any compound that contains lone pair is a Lewis base. Alright, so for example now, ammonia is a Lewis base. Water is also a Lewis base because water contains 2 lone pairs on oxygen. So those are the Lewis bases that we have. All right. So another thing, let's talk about acids. How do we identify Lewis acid? Okay, Lewis acid can be identified this way. Let's say, for example, let's say we have BF3. Now, same way we did for ammonia, pick out the central atom. Boron. Boron is atomic number 5. So let's fill in the orbitals. So I mean the configurations: 1s2, 2s2, 2p1. All right, so these guys, they're fill in the subshells. All right, so in this case now, we have 2 electrons. We have 3 electrons in the valence orbital. 3 electrons, and what happened here is that this p orbital is not stable, because for an orbital to be stable, it is either singly filled or fully filled. So these are the 2 conditions for p orbital to be stable. It's either it is singly filled or fully filled this way. So any configuration aside these 2 means that p orbital is not stable. Okay. So and p orbital want to attain stability, it means that it will undergo what they call excitation, whereby there will be a promotion of electrons from s orbital to p orbital. So electron will promote to this place, so which now lead to the formation of this stuff. All right, so we now have 1 electron here, 1 electron here, 1 electron here. All right, so in a nutshell, as you can see now that after the excitation, what happens? We still have vacant orbital. We still have vacant orbital. Vacant orbital. Orbital with no electrons at all. Whenever we do this kind of thing for any compound, and we find out that there is a vacant orbital in the central atom of that compound, it means that that compound is a Lewis acid. Therefore, barium fluoride is what? Boron fluoride is a Lewis acid. Lewis acid. Okay, so let's take another example. We can try this one to try BeCl2. So try aluminum chloride 2. So all these guys, they are Lewis acid. They are all Lewis acid. You can try them out to see that they are all Lewis acid. Okay,